Okay, so we're going to find the total mass of the solid between the cylinder y equals x squared that is bounded by these planes. Okay, so here's the graph of this parabola, but I've drawn it here with arrows, and that's not right because we only want the values of this parabola that are in between x is -1 and x is +1. Okay, so what we're going to do here is find the total mass of the solid between the cylinder y equals x squared, and then they give us all these boundary planes. I've done my best here to sketch out this object. So the first one is this cylinder y equals x squared. So you can see here I have a graph of y equals x squared for x between -1 and +1. And then since this equation doesn't have any z's in it, that means that this is the picture that you get for any value of z. And that's actually what makes this a cylinder, because a cylinder is any curve that is passed along a line. So you can see here, there's this, here is the curve right here. And then here it is again up here, and here it is right here as well. I mean, any z value has that parabola in it, so that's what makes it a cylinder. It's a curve passed along a line. And then they give us these other boundary planes, z equals 0 and 1. So that's what I've drawn down here. You can see here, this is the z equals 0 plane, and then up here is the z equals 1 plane. And then the last thing is the xy plane here. So that's the xz plane, excuse me. So that's this back wall back here. So basically you just have to draw all of the objects that they give you and then find out what is the shape that is in between them all, like in between and bounded by. So they're basically giving you a description of the walls and the floor and the ceiling of some kind of very strange house. Our solid is not uniformly dense. In fact, since the density is 1 minus z, this means the bigger the value of z, the smaller the overall density of the object. So I've tried to color it in here so that it is darker at the bottom. And actually the density would go negative if you went above the z equals 1 value. But that's okay in some applications because this may be charge density instead of mass density. The next step here for us is to choose the order, and I just want to point out that there is a bad choice here. I do not want to choose dx, dy, dz. You can see that actually from the formula here, because if I try to solve y equals x squared for x so that my limits of integrations can be x equals something, then I would have to end up with x equals plus or minus the square root of y. And this is just awkward, and I'd like to avoid it if I can. You can see it in the picture, actually. If I try to shoot a laser beam parallel to the x-axis, I would intersect the back wall here where x is equal to -1. Here's the region. You can see I actually enter the region enter the solid here. This is the 3D picture at -1, and then exit at the parabola, and then enter at the parabola again, and then exit again. So that's a bad choice. So I chose to set it up in the order dz, dy, dx, and so I imagined a laser beam shooting up parallel to the z-axis. It entered the region at z equals 0, and it exited the region at z equals 1. Then, so I actually am going backwards this way. This is the 3D picture, and then I'm stepping down to the 2D picture over here. The next one that I chose, I already did dz, so now I'm doing dy. You can see here dy enters at y equals 0 and exits at the parabola. So 0 to the parabola. And then I guess really there's also this is unnecessary, but there is technically a 1D picture from just on the x-axis from -1 to 1. So that's just this portion that I'm using right here. So that's where these limits come from. So the first step here is to calculate the antiderivative for 1 minus z, and I'm integrating with respect to z. So I got z minus a half of z squared. Plugging in these limits. Then now here you just plug in 1 here, you get 1 minus a half, and then the 0 all just goes away. Then now just an antiderivative of 1/2 with respect to y, so you get 1/2 y. Now again, when you plug in 0 here for y, that's just going to go away. So I basically just, the x squared goes in there, and then the rest of this just flows out. So I just want to talk quickly about the units here. So inside the integral here, what I'm calculating is the sum of a bunch of delta times dv's. So the units of delta are going to be kilograms per cubic meter, and then the units of dv, now that's just the volume of a very small box, so that will just be cubic meters, so these will cancel. So in the end, the final units here will be kilograms. Just a procedural warning here, you can see that these two functions have z equals, but there's no more z's on this side of the equation. And that's my first variable of integration here is dz. So you can actually see in this, all of the equals to parts of these equations, there's never a z in any part of them. The reason is because if there was a z left in this part of the equation, then I would be plugging it in. This would have a z in it, and then there's no place else anywhere in any of this for the z to go, which means there would be some kind of z in our answer, and that doesn't make sense because there shouldn't be variables left. This just needs to be a number. That pattern continues. You can see at this stage there is no z or y for the same reason. If we were left with a z or a y in at this stage, then there would be variables in our final answer. So you can see the last limit of integration has to only have numbers in it, because otherwise there's going to be variables left in our answer. So you can just always use that as a quick check. If you feel like something's going wrong, just have a look at it and make sure that each time you step backwards one integral, that there's no more of the first letter left. So in this problem, we're asked to find the total charge of a solid, and one of the solids is this cylinder, z equals 1 minus x squared. So I just want to talk briefly about how I graphed this. So I just graphed in the zx plane this downward facing parabola. There's the vertex of the parabola there. And then this doesn't have any value of y. You can see there's no y in this equation, which means this picture could be y equals 0, it could be y equals 1/2, it could be y equals 1. Any value of y, I will get this picture. And then since I'm only in the first octant, I'm actually only looking at this portion of it. So you can see here I have the y equals 0 graph. Here, right here would be the y equals 1/2. Here is the y equals 1. So all of these curves, basically you just take this curve, z equals 1 minus x squared, and you move it along the down the y-axis. That's what makes it a cylinder, because it's a curve moved along a line. Graph the plane y plus z equals 1. So here I graphed the x equals 0 slice of this plane. So that's right here. Then you consider the intersection of these two surfaces, this plane here and this sort of wedge, kind of curved wedge shape right here. So what's going to happen is when you slice these two, obviously this boundary right here is going to be included. And also we're the other boundary here is the XY plane, so we're also looking at this as being the floor of the object. So this is the bottom part of it. Then definitely this part right here is underneath the plane here. And then when the plane slices this wedge, you're going to kind of take a bite out of it like this, down that corner. So in the end, we're going to end up with a shape that's kind of like this. Let's try to make a choice here about what order we want to calculate this integral in. So this problem is interesting because I've chosen one here where the default order is not going to work. So if I try to shoot a laser beam in the z direction here, then right here I will enter at z equals 0, that's the xy plane, and then I will exit here on the walls of this kind of curved wedge shape. But then if I drew a separate dz, I would enter again at z equals 0, and then this time I would exit at on the equation of the plane. So that's awkward. I suppose there may be a way to set up some kind of very clever limits where you do go on to the integral and get the correct answer, but let's just choose a different order. This is kind of guess and check, so I'm guessing dx first. This kind of makes sense to me because when I imagine shooting the laser beam down here parallel to the x-axis, then it looks like I'm always entering at the back wall back here, and then no matter how I shoot it, it's always going to come out on the side of this cylinder here because this plane doesn't tilt up or down in the x direction at all. The guess and check method led me to dy, dz, dx. I tried dx first, and that seemed like it was going to work for a moment. It passed the laser beam test. I was able to shoot a laser beam and just enter and exit at one part of the figure. But then when I tried to calculate the limits, I ended up with x equals the square root of 1 minus z. I didn't like that. It's allowed. You probably could still get the right answer doing this, but if possible, I would like to avoid complicated expressions like radicals. There's domain issues. You have to consider whether or not you have plus or minus here and make sure that this all makes sense in the context of the problem. So I'm just going to try something else and see if that works. This seems like it's working here. When I calculated my limits, I solved this equation for y. You can clearly see that the laser beam shooting parallel to the y-axis would enter here where y is equal to 0. And then it's going to exit right here out the wall of this plane. So all I needed was a y limit that represented this plane. So I just solved this equation of the plane for y. I got y equals 1 minus z here. So that's where I got this upper limit. Okay, it really seems like it's starting to come together now. So since I already dealt with the variable dy, I'm going to need to somehow have a picture now that doesn't have any y's in it. So here is now a 2D picture. I'm done with this 3D picture. So here's a 2D picture that has only x and z in it. Now shoot a laser beam parallel to the z-axis since we're guessing dz next. This is going to enter the region here at z equals 0. and exit the region at this parabola, which would be the top part of this wedge shape in the 3D picture. So that's where z is equal to 1 minus x up there. All right, we got this now. So the last step here is to just consider the range of x's that we need to use in order to be inside the solid. So that's pretty obviously these x values right here. So that goes between x equals 0 and x equals 1. The way I got this was I just calculated the intercept. So this point where the region ends is where z is equal to 0. So if you put 0 here for z, then I think it's pretty clear that x is plus or minus 1, and I want the positive 1 on this side. Yay, we did it. We set up an integral to calculate the total charge in this solid, but nobody knows what a Coulomb is, and nobody cares that that one dude invented it. So that's the answer. Yay.